Today I'm going to be discussing about data acquisition, so collecting the data. So in the non-targeted analysis workflow, there's sample preparation, which is very important, including collection, potentially homogenization, extraction, storage, transport. All of these have very important effects on what we end up analyzing in our sample. Then we acquire that data, that extract, on an instrument. In this case, we'll talk about liquid chromatography, high-resolution tandem mass spectrometry, which will give us all of the data we need for the downstream steps of data processing and interpretation, which we will discuss in this tutorial series. So here's a general instrument configuration. This is actually for the Q-Exactive for thermo, but we also will show a general idea for the Q-TOF. Very similar principles. Now, we use liquid chromatography to separate ions. So in the case of PFAS, for example, the shorter chain PFAS will come first when we use reverse phase chromatography. So I won't go too in-depth into chromatography, but the basic idea is you have a column, it's packed with some material, your molecules stick to that material, and then you have a solvent that you change the solvent ratios until it pushes off your molecule from that column or pushes it out faster. And so often, for example, for reverse phase, which uses a C18 column, for example, so that's just 18CH2 carbon chain, then the separation will be based on polarity, with the least polar molecules being retained the most. So for lipids, for example, your longer chain fatty acids are going to come out last, and your shorter chain fatty acids are going to come out first. They're going to be separated out by lipid class. Triglycerides are neutral lipids, so they don't have a head group that's polar, so they're going to come out at the very end because they're more nonpolar. Whereas lysophospholipids, for example, have a polar head group and just a small chain, so they'll come out first. So depending on the molecule of interest, they're going to be separated out depending on some chemical property determined by what your column is made out of. So now, after separation, there's ionization. And then usually for high resolution instruments, there's a quadrupole. That quadrupole can be used to filter ions. So in a full scan mode, like we just showed, the quadrupole is going to send everything through within a certain mass to charge range. So let's say I did 200 to 1,200. Everything outside of that range will be filtered out so that you don't get noise from ranges that aren't analytically important to you. And then, of course, the next compounds will be coming out in time out of the column, and we'll measure those as well in the Orbitrap. And so you can see that our data is going to have a time axis on the y-axis and a mass of charge on the x-axis, and you're going to have a time and mass of charge. So this will be important when we talk about the different data that we have. And so this is the most basic data, is we get an accurate mass and we get a time from the column. Now, that will only give us potentially, with the time, if you're doing target analysis and you have a standard, you can get exact structure pinpointed by these GPS coordinates of mass, charge, and retention time. But non-targeted, usually we can only use the accurate mass to tell what that structure is, and it will only tell us what atom. So we need a fragment to break the molecule apart. In the Orbitrap, that molecule slams into nitrogen molecules, fragments into small pieces. The charged pieces of that molecule are then measured. And like Lego blocks, we now see all the pieces. If we have the manual, which would be the library, for example, we could look up each of these pieces and determine what the actual structure is. So this is MS fragmentation, which we can try to get for each of those GPS coordinates of MZRT, which refers to one molecule or a group of similar type molecules. Same thing for a Q-TOF instrument, or time of flight. They use different principles to measure mass, but the basic data we're going to get out is going to be very similar. So after separation in the column, let's say, for example, these two molecules, they have, if you counted it, a different number of carbons and fluorines, so very different masses, but they have a different, similar shape and size. They might coalute, which means come out at the same time. And so for that purpose, when we use the quadruple, we isolate a molecule before we fragment that molecule into pieces, for which we measure in the QTOF. So again, with the QTOF, it would be very similar. You can get your accurate mass scans, or you can fragment to get your fragmentation scans. Also with the QTOF, because of the speed, we can also include ion mobility, which we won't discuss here. So resolution is very important. So both QTOFs and Orbitraps are high resolution mass spectrometers. So this is showing similar data for the same sample. One's acquired on a high resolution instrument on the bottom and one's on a low resolution instrument on top. And you can see with the low resolution instrument, you only see a single peak. Whereas with high resolution, you can resolve more peaks. And so what we thought was one compound, as we increase our resolution, looks like 4 compounds. Actually, if you zoom in with your eyes and kind of look at these different peaks, you could probably see that there might be another compound. And if we increase resolution even further, there might be more molecules here. So this resolution is very important. And that's one of the parameters that we're going to have on our instrument. Here's the different resolutions versus mass to charge. So different instruments have different trends. So quadruple keeps the same resolution regardless of the mass to charge. Whereas for an Orbitrap, you actually lose resolution with higher masses. And whereas a QTOF, you actually gain resolution with higher masses and lose it with lower masses. So different instruments have benefits in different regions of the mass range. But generally, both QTOFs and Orbitraps give us the resolution we need for non-targeted analysis. Now, resolution is how well we can separate peaks. Mass accuracy, on the other hand, is how well we actually measure the mass compared to the theoretical mass. So if I know the mass is 200, and my mass accuracy is 2 ppm, I'd be off at 0.0004 Dalton. So how close are we to the actual mass that should be measured? Versus, so this would be a good resolution, and mass accuracy have to go hand in hand, because if you can't separate out the molecules, it's going to throw off the mass, and so actually going to throw off your mass accuracy. So assuming we have good resolution and mass accuracy, we would be in the center of this target. But if we have poor mass accuracy, but we still have good resolution, good precision, we could still get very close measurements. They would just be far away from what the actual mass is. And then, of course, if we had poor resolution but good mass accuracy, we could be everywhere, but we are centering around the right mass. So very important metrics. Resolution definitely affects the number of true positives we're going to get, and the number of false positives. So, for example, in this case, these are number of confident identifications. One is tentative, one is confident. And you can see as we toggle mass accuracy, so as we increase mass accuracy, or I should say decrease it, so we can measure mass less well. As you're moving to the right, we get more hits. These hits are clearly false positives because they didn't exist when we had better measurements. And so we know they have the wrong mass when we have better measurements, but when we can't measure those masses as well, we don't know. And so we'll get more false positives. So the better the resolution, mass accuracy, the less false identifications we'll get. So now we're going to be talking about the most important thing, I think, about this training as far as what you're going to be able to take home and use is the acquisition methods. It's very important, especially for suites of software, FluoroMatch, LipidMatch, PolyMatch, etc., that you acquire good MSMS data and good full scan data for the software to be able to have good data to work with. So there's a lot of different techniques out there to acquire MSMS. The most common approach, and definitely one that I recommend you always acquire on your data, is data-dependent analysis. This is a pretty simple method, and it can be called different things with different vendors. So some call it IDA, information dependent analysis, not to be confused with DIA, which we'll cover soon. But in most cases, people call it DDA, data dependent analysis, or DDMS2, data dependent MSMS. What this method does is at a single time in your chromatography, you're going to be measuring a full scan. So this is the full scan, meaning we haven't fragmented any of the molecules. And you can see the top 5 most abundant peaks in this case. So in data-dependent top N, which is the most common data-dependent approach, you take the top most abundant ions, you select them, and you fragment them. So the issue here, of course, is, let's say you're using an Orbitrap, which has relatively slow scan speed, 250 milliseconds on the old Q-Exactive platforms. They're getting a lot faster. And so you can get 60 scans in this chromatographic region. So the issue here is that there's 400 features. So if you can only acquire 60 scans at the resolution you want, collecting this amount of intensity you want, then you're missing about 1/8 of the features in this case. Or sorry, you're only getting about 1/8. You're missing about 7/8 of the features in this case. And so, for example, for lipidomics with biological molecules, those low abundant chemicals or species are often the signaling molecules that are more important for biology in some ways, and for your disease versus healthy. So you want to get those low abundant molecules. For environmental samples, the matrix might be really high. So even though you want to look at the most abundant toxins, the least abundant ones you might not care about, the matrix might be what's being fragmented, and you won't see any of your PFAS or your toxic chemical of interest. You can think of it as this girl pulling into this mystery box. She's going to pull out a few molecules that she's able to identify, but she doesn't know what she's going to get, and she's missing. And we want to be greedy, and so we want to make that little boy who runs over and is greedy and grabs all the things out of the boxes, so we have everything. We want to know what all the molecules are. So there's different approaches for this. So we talk about auto MSMS, which is on the right here, where you only get a narrow region of the mass to charge range that we fragment. And so we don't cover the entire mass to charge range, which means that we are missing molecules when we're isolating fragmenting. There's also something called all ions or all ion fragmentation. And in that case, the most common approach is you use a full scan where you acquire all of your MS1 data or your intact molecules. And then following that, you get an MSMS scan, but instead of setting your quadrupole to select a single Dalton window for a single molecule, you set it to your entire mass range and fragment everything simultaneously. So now we can be greedy and grab everything out of all of those cups and see what we get. Then there's hybrid approaches. All of them sometimes have very different sophisticated methods in which they acquire MSMS, but the general idea is that you either form a gradient across all your mass charges or smaller windows, and instead of isolating everything and fragmenting everything simultaneously, you have smaller, let's say 100 Dalton windows to fragment so that there's less overlap of other ions in your fragmentation spectra. The fragmentation spectra is only for what's in that 100 Dalton window, a little bit cleaner. So it's a hybrid approach between the right and the left. Neither of these approaches are great. The Q-ray / SWAP, that DIA method, or the all-ion method, because we have overlapping fragment ions from all the other molecules in that region rather than just a single Dalton region. So, in my opinion, in this training video, I guess I have a very strong opinion that we use iterative exclusion or intelligent acquisition. So a lot of vendors such as Agilent have built-in iterative exclusion, and Thermo, you have to pay for it, but you can get Acquire X, which is an intelligent acquisition method on their instruments as well, where you can use information from a prior injection to determine what you get MSMS in the sequential injection. So in the most simplest case, you take an initial injection, and again, now we only get the top 5 most abundant ions. We're missing most of our ions. In the next injection, so we're literally re-injecting the sample onto the instrument, acquiring it all over again. And at that time point, we create an exclusion list. So it's excluding those top 5 most ions that it selected last time and getting the next 5 most abundant ions. Now we can repeat this process, usually in positive ion mode. I might do it 5 or 6 times, in negative mode 3 or 4 times, depends on the complexity of your sample, how many peaks there are to go through to get to that bottom, where you've got MSMS on most of your peaks with good analytical signal. But you can repeat that process and then get the next top most abundant ions and the next top most abundant ions, placing each previous run on an exclusion list. So here's an example where there's some diminishing returns, but you can see all of the novel or new annotations, A's being highly confident annotations using our software, as we go through 4 injections of a sample and use iterative exclusion. So you get a lot more annotations, more than doubling the number of annotations using this method. For PFAS in this case, lipids, and some complex matrices, you get even more improvement because of how many ions there are, how many lipid ions, and how much they're competing for signal. So you definitely want iterative exclusion for lipidomics. Very important. The other thing about getting MSMS is how many full scans you get. So let's say we do a bunch of MSMS scans, and then we do a full scan, and then a bunch of MSMS scans, and let's say we get really high quality MSMS, want to average it a lot across a QTOF, or get a very long time in the Orbitrap to get very high resolution. Then there's a long time between full scans, and so we don't get many full scans across a peak. And you need, I would say, roughly minimum 10, 11 full scans across a peak to get good integration, to peak pick and find these peaks. So in that case where we don't, so for example on this diagram on the left here where we only get 2 full scans, in that case, then we need to acquire a separate full scan from our MSMS data. If your data dependent is fast enough and you have less scans across of it, you can use your data dependent data as your full scan data as well. This is definitely recommended if you have very large data sets where you expect each sample to be different. So for environmental samples, often we'll want data dependent analysis across every single sample because every single sample is different and one could have a toxin, and that's still important even if all the others don't. Whereas in lipidomics, we might just pool samples and get MSMS data, and the rest we acquire in full scan only to get very nice number of scans across a peak, because lipids are lipids, blood is blood. Even if it changes across disease type, we don't expect it to completely disappear, or we can pull the different disease and healthy, etc., and run MSMS on that. So we don't need MSMS in every single sample for biological measurements usually. For all ion fragmentation, we alternate between full and AF. So the nice thing here is not only do we get full scans across the entire peak, and so we could definitely use this for quantitative analysis as well as for peak picking, finding those peaks in the MS1 dimension, but we also get consistent fragments across all molecules over time, which can be very useful as well. It's useful. So for example, this is leachate foam. This is PFAS data, and you can see different fragments over time. So I can look for C2F5-. I know this is a common fragment for PFAS, and I can see traces for C2F5- in my all ions data across time, and I know then that there's PFAS at that time point, at least one PFAS. And so if I use my non-targeted analysis and I've identified in green number of compounds, then I can see in red the ones that were not identified, but I know that exist based on my all ions. In a complete non-target approach, I'm just saying what has a carbon-fluorine chain in this case because it gives a C2F5-, and I can see that I've missed a couple of peaks, and I can go back and find those molecules. Also, you can see in gray that depending on the fragments, if you don't choose all of the fragments that are possible, you might miss some molecules. So you both want to identify using the whole software workflow, which we talk about later, but you can also use the all ions to determine if you've missed anything. Same thing for lipids. So for example, this often we'd want to use negative ion mode and look for the fatty acid. So if I want to see all the lipids that gave 20:4 arachidonic acid, I can look for that RCO-, that fatty acid fragment, and look at the trace across my entire chromatogram and make sure I haven't missed any species that have 20:4, maybe even discover new species of lipids that have 20:4. So, when you mix up your Lego sets, you have a problem. So this is a Lego analogy. So we talk about data-dependent analysis. You only have fragments from that set, from that molecule, unless, of course, there's molecules that overlap at one delta. But let's at least say you're more likely to only have fragments related to that molecule. And so let's say you had an instruction manual, which would be your library. You know which pieces belong to your set. You can easily say, okay, with these pieces, this is the Lego set that I have. This is the ship. And so you can easily tell from the fragments of the molecule what the molecule is using DDA, especially if you have a library. DIA is a lot harder because instead of taking one Lego set, you have all your Lego sets, and let's say you leave them out at night, your toddler stumbles out of their bedroom, as they will in the middle of the night, sees them sitting on a counter just within reach, scrapes them all off onto the floor, spends the night shredding them into pieces, taking them apart, and now you have all the pieces. So not only do you, when you wake up, do you step on them, maybe curse, as they hurt your foot when you wake up in the morning, but as far as the molecules are concerned in this analogy, you have fragments, but you don't know which Lego set each one belongs to, and you have to like sort and figure out which fragment belongs to which molecular set to be able to identify these, which is quite difficult. The way we do this, so this is an example for PFAS, but works for the same for all other molecules, is we're going to take a fragment, let's say a neutral loss of the carboxylic acid, or one of the carbon-fluorine chains. So here's the neutral loss of the carboxylic acid, and you can see that it correlates with this red EIC, which is the precursor. And this is what you'd expect, right? So you'd expect if I have a molecule coming out of my chromatographic column that it's going to form a certain shape, and if I'm fragmenting it, the fragments are going to form that exact shape because as that molecule goes up, so will the number of fragments that occur. As that molecule goes down, so will the number of fragments. So even you see the little dips, everything looks exactly the same. So mathematically, we can use regression or Pearson correlation or something like that to determine whether that fragment belonged to that precursor mass. Do note, as we showed earlier, that a lot of these fragments, such as C2F5, occur in multiple places and may overlap from many different ions. So this is going to make the job a lot more difficult, especially let's say we're looking at fatty acid and lipids, and so many lipids have 20:4. It might actually not correlate with your precursor ion, even though it exists, because there's just so much overlap from all the other molecules, so you can't use this correlation. So you actually, when you're using all ions, surprisingly, don't get more identifications after this filter, but actually get less because of this issue in deconvolution. We do have a workflow, both a standalone and built into our software called IE-DDA, coded by Michael Kumer. And this software, you can either bring in your files and generate a deconvoluted version of that file, so it looks just like a data-dependent version using the deconvolution we talked about with the correlation. Or it's built into the software, so when you use all ions files, it will automatically deconvolute for you. So there's a lot of reasons for false positives in MSMS acquisition. So this will be important later on when you're trying to confirm species. One is chiral spectra. What this means doesn't have anything to do with right-handed or left-handedness, but this means mixed. So we may have a spectra, especially for all ions, obviously this is a problem, but even for data dependent, if we have a 1 Dalton window, sometimes multiple molecules fall within that 1 Dalton window. And if they're similar intensity, then the fragmentation spectra we get is from both molecules. So which fragment came from which molecule? Again, that same difficulty. So we could get false positives if we got fragments that look correct, like, oh, I have some C2F5, so this is definitely a PFAS, but it actually came from a different molecule co-isolated. There's also, of course, random noise above your noise filter, so you could get noise or background intensity in that fragmentation scan or full scan data and get false positives in that way. So obviously you can limit your false positives through higher resolution in case those peaks that we're thinking are C3F7 or C4F9. As you get, for example, larger in mass, there's more chance that other formula will overlap. So with high resolution, we'll be able to separate those types of false positives, not if it's the exact same molecule from a chiral spectra. We can use intensity patterns to deconvolute spectra, as we talked about before. And we can also reduce fragments to only those from the precursor ion using correlation, for example, such as in all ions that we talked about. So the important point as we talk about all these ways of acquiring MSMS data for lipidomics, as it shows here, or PFAS, etc., is what's the best way to acquire. So I think iterative exclusion data dependent is because not only are you getting MSMS for almost all your ions, but it is quadruple isolated MSMS. You're getting a 1 Dalton window MSMS, so it doesn't have all those problems we talked about with all ions. So definitely want that. Still, you can use some intelligent acquisition methods. Those can be even better than iterative exclusion. And then still you can supplement with DIA. I wouldn't only acquire DIA data again for your data. I would definitely get data dependent or some kind of intelligent acquisition data dependent data as well, because it can be very hard to confirm species with just data independent acquisition. And then we'll talk about the sequence as well. So when you're acquiring data, just to summarize, you want your full scan data having at least 11 scans across your peak. You want good MSMS, usually data-dependent or iterative exclusion, and you can supplement that with DIA. Now, for your sequence, what you're going to run, we want to always have some blanks. Solvent blanks will tell you what contamination is coming from your instrument, from your chromatography, so on and so forth, from your solvents. And then you also want extraction blanks or field blanks, things that have been carried through your entire workflow. These will be very important later on in the software steps for removing things that did not come from your sample, but rather came from your glove or from the instrument or from your solvent that you don't want to consider as real. Also, you want a field blank that you carry through. You store at the same freezer at the same time. You transport it in the same way. The only thing is you just don't put sample in it. You acquire it randomly throughout your run. As you can see between runs 5 through 10, for example, you can run always a field blank. In the case of lipidomics or something you might want to pool with MSMS. In the case with environmental samples where they're all different, you might want to take the highest abundant ones and do MSMS on those. For MSMS acquisition, you can go deep with the IE on a pool. Again, this would make more sense for biological samples like lipidomics or high-level samples where they're all very similar, such as AFFF, just the same lot of AFFF or the same brand, different lots. You might want to pull that together and do iterative exclusion. For other environmental samples, you might want to do iterative exclusion by running each sample sequentially. So let's say you have 100 different surface water samples, you can run those in batches of 5 to 10 and run your iterative exclusion from sample to sample rather than reinjecting the same sample. And then with some instruments such as Agilent or Thermo, you can set a threshold. So if it did acquire MSMS previously, but in your new sample you have much higher PFAS, for example, let's say it's 10 times higher. So you want to get MSMS again to get better quality than the low MSMS you got before. It can do that as well. So it can get new MSMS of the same molecule to get better quality, as well as getting new MSMS of different molecules. So with that, we have covered acquisition methods, how we acquire data using liquid chromatography, high-resolution mass spectrometry, our sequence, how we might want to put our samples on our instrument, and the different scan modes, MSMS, full scan, etc., that we might want to acquire. A last note here is we haven't talked about polarity. So in most cases, let's say you're doing PFAS, you might only run a single polarity, negative polarity mode. Polymers, maybe you just run positive polarity mode. And in that case, then this is irrelevant. But let's say you're running lipids and you have both positive and negative mode, or you want more coverage in PFAS for AFFF. They have some molecules in positive mode, not many, but some. So you want to run positive mode as well. So you can do this sequence the same, and you can run your positive mode, then your negative mode. Or you can do polarity switching, which switches between positive and negative mode. In that case, you probably only want to acquire full scan data, not do DDA for the samples when you're doing polarity switching to make sure, again, that you have 11 or more full scans across a peak. Lastly, as far as randomization goes, one of the challenging parts of mass spec is getting reproducibility. If I run the same data or sample a week later or a year later on the same instrument, even using the same methods, the background on my instrument is going to be different, so I'm going to have a different contamination. A lot of my chromatography column might be different, or solvents. So there's going to be different background. The retention times are often going to be slightly different. Even the abundances, the efficiency at which the instrument's measuring and giving signal abundances might be different. And so you want to make sure that your samples are randomized across batches and between batches. So if you have 100 water samples and you're comparing one upstream and one downstream of an industry, you want to make sure that those are randomized. If you have a disease in a healthy individual, you want to make sure those are randomized so that if there are batch effects, then, and if let's say you do batch 1 all your controls and batch 2 you do all your disease, and there's batch effects, you don't actually know whether the changes you're seeing in your lipid profiles are based on your disease or based on the batch effects. But if they're randomized, you can look within a batch and see if you see the same differences, and then it's not based on batch effects. If you randomize within a batch, then it's not based on run order, which can affect signal. So you want to randomize your samples as well. Okay. You might also want a reference material. So something that's well characterized, that can be your quality control. There's a lot that can go into this QC. Obviously, I'm not describing it in full depth, but just giving you some ideas, minimum ideas for what you could run that would be helpful. So if you have a reference sample, you know what should be identified in it, you know what it should be look like, then you can troubleshoot if anything's changing across your instrument or from run to run. So with that, I'm going to close this tutorial. I hope you guys learned a great amount. Please feel free to ask questions in the comment sections or reach out to me. Go to innovative omics.com. There's more resources in the tutorial description. Thank you.